Oh boy.
Okay. Hi, everyone. Thanks for coming and thanks for the invitation. I'm very excited to share relatively recent work that was done at BioCars to kind of develop mix-and-inject serial synchrotron crystallography. So just to get started very briefly, if my thing will advance. No. Okay. So I'll briefly go over the differences between traditional crystallography and serial crystallography, but I'm sure with this audience, I don't need to spend too much time on it. But the big difference is, with traditional crystallography, you're usually getting data from one or a few crystals. You have one crystal mounted up on a goniometer and you're rotating it to get all of the different orientations, to get all of the information you need to get a complete data set. And of course, for your crystal to tolerate this amount of radiation damage, you're typically doing this under cryo-cooled conditions, which has the downside where you sometimes are getting biological conformations that are not as biologically relevant. So, relatively recently, serial crystallography has been kind of revitalized, and the concept there is that you have a bunch of crystals that are all randomly oriented, and you're getting a single diffraction pattern or diffraction pattern still from a single orientation of a crystal, which means you get a lot less information per frame, of course, compared to something like traditional crystallography. And to compensate for that, you have to use many, many more crystals. But the upside here, of course, is that you can do these measurements at room temperature, which allows for studying proteins in their more biologically relevant state, and then also leads to the ability to study things like protein dynamics with various time resolve techniques. So there's kind of two main flavors of time resolve techniques. The first, very broadly, being pump probe, which uses a laser to trigger some type of reaction. This is very successful for a lot of photoactive events, but unfortunately most proteins are not, natively photoactive. So there's been a lot of work on expanding the reach of this technique with things like photo cages, where you would have a photo cage linked to a ligand to release it, or even things like temperature jump, right, where you're using lasers to, trigger just more broad dynamics in a protein. And then in addition to this, pump probe category, there's mix and inject serial crystallography. And this is a really widely applicable technique, because the way I like to think about it is you're looking for, your protein to interact with basically any small molecule. So this has applications for things like just ligand binding, catalysis, drug design, really any interaction that involves, a protein and a small molecule. And that's what's really exciting to me about being able to do mixing experiments. There's just a lot of different types of experiments that you can do. A lot of this work, and the way I'm showing it here, was originally pioneered at X-ray free electron lasers, but of course there are only 5 active XFELs in the world, which really limits how many of these types of experiments can happen. So, there's been a lot of work and already a lot of successes in serial crystallography at synchrotrons. And, part of that is due to there being so many synchrotrons around the world, so many synchrotrons starting to develop beamlines. And there's also been a lot of efforts in time resolved, but, mixing has kind of been something that's still been in development for serial synchrotron crystallography. So it's been something that we've been interested in. And to me, the big difference is when you're doing a serial crystallography project at an XFEL versus a synchrotron relates to the differences between an XFEL and a synchrotron. So I'll kind of briefly go through that. But at an XFEL, right, you're getting 10 to the 12 photons in as short as, tens of femtoseconds, which are obviously really short interaction times. And one of the most common ways, or perhaps one of the most popular ways to achieve this, is by using a liquid jet. They can be produced by a variety of means, but here it's produced by a gas dynamic virtual nozzle. And what this does is, of course, your jet is moving extremely fast, on the order of tens of meters per second. So it's able to accommodate these really short exposure times and deliver fresh crystals for each subsequent pulse. But if you think about, a synchrotron, you're more so getting, let's say, 10 to the 9 photons in 10 milliseconds, which means it's really difficult to actually use a liquid jet directly at a synchrotron, because the jet is moving really fast and you'd want to keep the crystal in the observation region for, maybe on the order of 10 milliseconds, which is just not really feasible with how fast the jets move. So instead, what we've developed is this Kapton based flow cell. And I will talk more about that, the details of that in a moment. But the key here is that you can slow all your flows down to more on the scale of being on the millimeters per second scale, which means you can keep your crystal in the X-ray beam for as long as you need to kind of accumulate enough flux to get a good diffraction pattern. But of course, and especially this crowd knows, there's other options at a synchrotron. These stats are mostly for monochromatic synchrotrons and honestly maybe a little out of date, with things like ESRF. But instead, of course, at a polychromatic source like biocars, you can get a lot more flux in a lot shorter of amount of time. Something on the order of, let's say, 10 to the 10 photons in 24 pulses, which is as short as 3.6 microseconds. So that's a real benefit. We're getting more flux, but there's some other benefits, of course, to doing Laue crystallography. And that, the best way, in my opinion, to explain that is to think about the diffraction events themselves. So if you think about a monochromatic diffraction event, you have your single Ewald sphere, which corresponds to, of course, like your single X-ray wavelength. And you get, diffraction events when you have this intersection. But when you have a polychromatic experiment, you now have multiple Ewald spheres because you have multiple X-ray wavelengths, which means you get a lot more information per shot. And the benefit to this is now, instead of needing something on the order of thousands of patterns to get a complete data set like you would with a monochromatic experiment, you now can more so need hundreds of patterns. So this is also another benefit when it comes to things like sample consumption and ease of experimentation and experimental efficiency. So now, I'll go back to the sample cell itself. This is just an example of the static design. And basically the way that this works is that you have your crystals coming in through a normal capillary, and they're sheathed on either side by an external flow. I have written water here. Obviously, if your crystals can't tolerate that, we'll put some type of mother liquor, whatever your crystal needs. But in this Kapton observation region, they're in, the co-flow regime. So basically you have your crystals coming in a centralized stream, and then you have, some type of sheath on either side just to keep the crystals off the side of the walls. And you can adjust your flow rates, whatever you need, and you just park your beam here and get all of your diffraction patterns. So that's the static version of this. And of course, we did a lot of proof of principle testing before we went much further, but this works really well. We can get high quality diffraction patterns while flowing in this Kapton based cell, but we were more interested, of course, in doing this in a mixing way. So what I basically did is I took our same microfluidic mixer that we use at the XFEL, and I'll explain more in a moment, and coupled it directly to this Kapton observation region that you see here. So here the crystals are basically shown in red, and the first step of this mixer is this key focusing region that you see here. And what's happening in the focusing region is that as the crystals exit the capillary, there's a small gap before another capillary starts. They're exposed to an external sheath flow that you see here, and it actually carries your ligand, and it flow focuses the crystal stream down a really thin stream. And this is what's really key to this, because they're based on, hopefully my audio is okay. I'm getting weird messages on my computer, but what's happening here is as you flow focus down more, you can diffuse your ligand in faster. So basically, the more you flow focus down, the faster your diffusion, because of course diffusion scales with the square of the distance that you have to diffuse over. So that's this first key step. And then the next thing that happens is this mixing. Let's see. Okay. And in this mixing stage, what's happening is your ligand is diffusing into the sample stream. So that means the concentration of the ligand is increasing in the sample stream, as you're progressing, because you just have your ligand diffusing in, diffusing in, diffusing in. And at some point, we can consider the system fully mixed. And we typically consider the system fully mixed when at the center of the sample stream, the protein and the ligand are equimolar or 1-to-1, right? So we, calculate the concentration of the ligand at different, streamlines in the sample stream, and we keep track. And when they're equimolar at the center, we can consider the system fully mixed. We then let the system age for an additional delay time before we eventually probe it. And this is basically also how we calculate our final time point. The really nice thing about the flow cell design is that in addition to changing the flow rates to get to different time points, we can also change the position of the X-ray beam relative to the tip of the mixer to get different time points. So effectively, we can keep aging the sample in the Kapton observation region and then probe it somewhere else. And what's nice about this is that you can get really wide ranges of time points out of a single device. So the experiment we did most recently, I think it was about 50 milliseconds out to 3 seconds, and the data I'll show you in a moment was 3 seconds out to 30 seconds. So you can get really lots of different time points from a single device, which makes it really easy, of course, when you're doing the experiment. And you're just changing your flow rates, changing the position of your X-ray beam, or really moving your sample cell, right? And then collecting more data and starting your next time point in less than 5 minutes. So it's makes the experiments really efficient. So now we have our mixer. We want to do, an exciting biological experiment. So before I do that, I'll show you the fun videos if they'll play for me. Let's see. Come on. Oh, let me take this off. Okay, there it goes. So this is the focusing region that you see here. So that's the crystal stream coming down the middle, and they're being flow focused down. And then in this video here, that's the crystal stream in the Kapton observation region. So that's a very, very dense crystal stream. We wouldn't use that high of a density when we're actually collecting data, but just for demonstration purposes, that's basically what it looks like with all the crystals streaming through in the Kapton observation region. So now, right, we have a working device. We want to do some exciting biology, and the system we've been studying is DJ-1. It's a redox regulated protein linked to lots of different things, including Parkinson's disease. And actually the structure of DJ-1 has been studied for a long time, but what's really been disputed is its enzymatic activity. So it's been a debate whether DJ-1 acts as a glyoxylase or a deglycase, and I'll kind of go through each of those cases now. So in the case that DJ-1 acts as a glyoxylase, basically DJ-1 is acting directly on this substrate methylglyoxal to convert it into lactate. So that's kind of the first hypothesis. And in the case that DJ-1 acts as a deglycase, it instead acts on this methylglyoxal adduct, this hemethioacetal species, and DJ-1 deglycates or removes the methylglyoxal and converts it into a lactate. So that's these kind of, two different competing theories. And as you can see, there's nothing really spectroscopically active in these species. So it's been difficult to kind of discern which process is happening. And to add a little bit more complexity to the story, this hemethioacetal species is in a reversible equilibrium, meaning that in the case where DJ-1 is a glyoxylase, as it's consuming the methylglyoxal, it's also shifting this equilibrium kind of in this direction, and you're seeing the disappearance of the hemethioacetal species as well. So it's been kind of, difficult to discern what is happening, what is due to an enzymatic activity of DJ-1. And that's where it's really beneficial to have a technique like mix-and-inject crystallography, where we can try to capture direct structural evidence of DJ-1 acting on methylglyoxal. So basically the experiment we did was we had these wonderful DJ-1 crystals that were produced by Cole Dollimore and Mark Wilson's group at University of Nebraska-Lincoln. We mixed in the methylglyoxal and we captured a variety of time points ranging from 0 to 3 seconds, and we had to see if we could get evidence of any type of reaction happening. So briefly, I'll talk about our data analysis pipeline where I show you some results. It's going. Oh, sorry. My computer froze for a second on my end, at least. So our data analysis pipeline was that we, had all of our diffraction patterns, and we had help from Vukitsa in, using precognition for all of our hit finding, indexing, and integration. But then for the scaling and merging, we use Careless, which is a relatively new program developed by Kevin Dalton and Doga Hexter's group at Harvard. And the really beneficial part to Careless is that it puts all of your time resolved data on the same absolute intensity scale, which is really important for all the difference maps I'm about to show you, right? So we had a lot of success using Careless, and we were really happy to work directly with Kevin to implement that. So, as a very rough first pass, I'll just show you 3 time points, and we see these green blobs in the center from all of these difference maps, right, where you take your time point and you subtract off the 0 second time point. And this is a positive density that's left, which corresponds to methylglyoxal. So that's already a good sign, right? We got our ligand into the crystal, and it's there at these time points. And the other interesting thing, of course, is that these these density blobs are situated very close to the cysteine 106 residue, which was expected to be the catalytic cysteine. So that's also was a very interesting kind of first step. And now we'll zoom in a little bit on this 10-second time point, and we can actually, model in the methylglyoxal very convincingly and actually model it as a hemethioacetal intermediate species. So what this basically is showing is we see DJ-1 acting directly on methylglyoxal, which we believe is kind of the first step in confirming that it has direct glyoxylase activity. And now past that, we're really focusing on trying to answer some key mechanistic questions, right? So in this 10-second time point, we see the first proposed step of the mechanism, which is forming this hemethioacetal species. And then in later time points, we see what we believe it is a transition to kind of the next intermediate, this enediol species. So we're really excited in the sense that these results kind of confirm the enzymatic activity of DJ-1, and now we're also able to answer some mechanistic questions. And I'll kind of close with some thoughts about sample consumption. So all of this data was collected at BioCars with the Rayonics, which has a 10 Hertz data collection rate. Our sample flow rates for the crystals kind of range from 0.8 microliters per minute to 4 microliters per minute. And we were getting data sets, kind of ranging from 1 to 4 hours, which means we're consuming somewhere between 100 and 1,000 microliters per time point. But honestly, it's closer to that 100 microliter consumption number, because when we're flowing at higher flow rates, we're actually collecting data in a shorter amount of time because you have more crystals per unit time. So, really not bad. And we are collecting about 2 to 4 time points per day, which this 2 to 4 time points per day is not far off from how efficiently we collect data at an XFEL. But of course, now we're consuming a lot less crystals. So we're already pretty happy with this. But before the shutdown, I got to play with the EPIX, which right now works up to 247 Hertz at BioCars. So let's just think about these numbers collecting data 25 times faster. So if we keep our same sample flow rates, we could now get data sets in as fast as, let's say, 2 to 10 minutes, consume as little as maybe 40 microliters per time point, and probably collect on the order of tens of time points per day, which is probably faster than you can actually think. That's how I felt when I was using the EPIX, but it's really exciting to think about where this technique could go with faster data collection rates. So with that, just a quick summary, I showed you our mixer for doing mix-and-inject stereocrystallography at a synchrotron and how we used it to study the really interesting biological system DJ-1 to really confirm its enzymatic activity and start to answer some key mechanistic questions. And of course, this experiment was done extremely collaboratively, especially with Cole Dollimore and Mark Wilson at University of Nebraska Lincoln, at BioCars with Rob making sure all the hardware was working for us, and Bukitsa with all of the data analysis, and then also directly with Kevin to use Careless. And with that, I'm happy to take any questions.